Hi everybody, in this video we are going to start talking about probability. Probability theory is the study of the likelihood of events. So when we talk about an event, we're talking about anything that could happen. So for example, the Yankees winning the World Series, that can be an event. Or it rains this afternoon, that could be an event. Or I beat my brother in a game of chess, that can be an event. Okay, and when we study probability, we're asking questions such as how likely is it that the Yankees win the World Series, or that I beat my brother at chess? Is it impossible for me to beat my brother in chess? Is it just unlikely? So maybe it probably won't happen, but it could, it might happen. Okay, is it definitely going to happen? These are the kinds of questions that we ask when we do probability. Now, mathematicians quantify the likelihood of an event occurring by putting it on a scale from 0 to 1. So that would be in decimal form. And usually when we talk about probabilities, we do keep things in decimal form, but you could also do it in percent form. So in percent form, that would be on a scale from 0% to 100%. Okay, so 0% is the lowest. You can't have a probability that's lower than 0, because 0 already means it's impossible. Can't get any the likelihood of an event can't get any less than being impossible. And a probability of 1 or 100% means that something is definitely going to happen. It's certain. So you can't get any higher than that. If it's already certain to happen, then that's as high as you can get. Okay, there's nothing greater than that in probability. Okay, so let's start going back to the low end. If the probability of an event is 0, or as a percent, 0%, then it is impossible for that event to happen. So let's take a look down here at this example. So this says it is impossible. So imagine that we have a crate or a box here which is filled with marbles. And you can see that in this case, all of the marbles are blue. Now I'm going to close my eyes and reach into that box and pick out a marble. And I'm going to ask myself, or maybe beforehand, before I reach into the box, I'll ask myself, okay, how likely is it that I pick, say, a yellow marble? Well, you can see that there are no yellow marbles in that box. They're all blue. So it's impossible for me to pick a yellow marble. And that's what I wrote over here. It is impossible for a yellow marble to be picked. Now, here's sort of in mathematical notation how we would write that. We would say, write P and then in parentheses yellow. So that stands for the probability of picking a yellow marble. And you can see that I set that equal to 0 because there are no yellow marbles there. It's impossible for me to pick a yellow marble. So the probability of picking a yellow marble is 0. Okay, moving on to the next example. If the probability of an event is greater than 0, but less than 0.5, or as a decimal, that would be 50%. So it's bigger than 0, but it's still less than 0.5. Then the event is unlikely. So for example, over here, you can see that I have another box with a bunch of marbles in it. Some of the marbles are blue, some of the marbles are yellow. You can see that there are more blue marbles than yellow marbles. But unlike before, I do actually have some yellow marbles this time. So is it impossible for me to pick a yellow marble? No, I could pick a yellow marble. If I close my eyes, reach my hand into that box, I might get a yellow one, but it's still unlikely because there are few yellow marbles in that box. So we would say that the probability of picking a yellow marble, well, I wrote here, it is unlikely that a yellow marble will be picked. So the probability of picking a yellow marble in this case would be greater than 0. So it's not impossible, but it would still be less than 0.5. Okay. We'll talk about what 0.5 means next. And also I want to let you know, is it possible to calculate the probability exactly? So I know it's between 0 and 0.5 somewhere. Can I say exactly what the probability is? Yes, and we will talk about that in a few minutes. But let me just move on to the next example now. Okay, so what does it mean for a probability to be 0.5? So if the probability of an event is exactly 0.5, or moving the decimal point 2 spaces to the right, that would be 50%, then the event is just as likely as unlikely. So for example, over here, you can see that I have another box with some blue and yellow marbles, except this time there are exactly as many yellow marbles as blue. I have 1, 2, 3, 4 yellow marbles, and I have 1, 2, 3, 4 blue marbles. So it is just as likely for me to pick a yellow marble as for me to pick some other marble. Okay, it's exactly the chances are exactly the same that I pick a yellow marble or that I don't pick a yellow marble. Okay, so it is just as likely as unlikely that a yellow marble will be picked, and we can write the probability of picking a yellow marble in this case is equal to 0.5. All right, next example. If the probability of an event is greater than 0.5, but less than 1, so in percentages greater than 50%, but still less than 100%, then the event is likely. Okay, so that means it probably will happen, but it might not. Okay, actually going back to this example, back here, I don't remember if I said it, but if something is unlikely, another way of saying that is it probably won't happen, but it might. Okay, that's if it's unlikely. And being likely is just the opposite. If something is likely, that means it probably will happen, but it might not. Okay, so for example, we have another box filled with marbles here. You can see most of the marbles are yellow, but they're not all yellow. I still have one blue marble there. So if I close my eyes and reach my hand into that box, am I definitely going to get a yellow marble? No, not definitely. I might get the blue one, but I probably won't get the blue one. I probably will get a yellow marble. So it is likely that I will get a yellow marble there, but it's not certain yet. Okay, because it's still possible that I don't get a yellow marble. So it is likely that a yellow marble will be picked. And you can see here the probability of picking a yellow marble will be somewhere between 0.5 and 1. And you can see that I'm using strict inequality symbols. So you can see that I did not put the line under these inequality symbols. Ooh, let me change that. I didn't put a line underneath these inequality symbols, okay? So that was on purpose, okay? Because I don't want to say, if something is likely, then I don't want to include the possibility that the probability is 0.5, because that would mean that it's just as likely as unlikely, okay? Not that it's likely. And so I didn't put that line there. And I also don't want to put the line here, because that means that the probability of picking a yellow marble could be 1. But if something is likely, that means that it's not certainly going to happen. The probability can't be exactly 1. Okay, so that's why I didn't put the line there either. And going back to this example over here, again, I'm using the strict inequality symbols. I'm not putting the lines underneath there, because if something is unlikely, it can't be 0, it can't be 0.5. It has to be somewhere between those numbers, not including these numbers. Okay, same thing over here, not including the 0.5 or the 1. Okay, so let's move on to the last definition here, the definition of something being certain. If the probability of an event is 1, or as a percent, that would be 100%, then it is certain. So you can see here I have another box with some marbles, but now all of the marbles are yellow. So if I close my eyes and reach my hand into that box, I'm definitely going to pick a yellow marble. Okay, it's not just probable, it's not just likely, it is certain. It must happen that way because there are only yellow marbles in that box. So it is certain that a yellow marble will be picked. And in this case, the probability of picking a yellow marble is equal to 1. Okay, it is certain to happen. All right, now I told you that we would actually, so for example, back here for this one, if something is likely, I know it's between 0.5 and 1. I know it's somewhere in there. Can I say exactly what the probability is? Yes, I can. So let's talk about how to calculate probabilities now. Okay. So to calculate the probability of an event, take the number of ways the event can occur and divide it by the total number of possible outcomes. So a quick way of remembering that I like to say is good over total. So what does it mean for an outcome to be good? Well, we get to decide what we consider to be good and what we consider to be bad. So in this case, a good outcome for us is picking a yellow marble. That's what we want to happen. So we're going to count all of the ways that we can pick a yellow marble and divide by the total number of things that could happen, which in this case just means the total number of marbles that are in that box. Okay, so let's start with the first one over here. Okay, it is impossible for a yellow marble to be picked. So we already know that if there are no yellow marbles in here, then it's got to be impossible. And something which is impossible has a probability of 0. So let's just confirm that this definition of probability, good over total, is consistent with what we just said. So in this case, using good over total here, we should get a probability of picking the yellow marbles as 0. So let's see if we do. So the probability of picking a yellow marble should be the number of good things that could happen. So how many yellow marbles are in here? Well, there's 0 yellow marbles in here. So that's going to be the numerator of our fraction, 0, because there's nothing good here. If we want a yellow marble, then all of these marbles are bad for us. So there's nothing which is good in this box. Now, what about the total? The total number of marbles in that box is 1, 2, 3, 4, 5, 6, 7. So we'll put 7 in the denominator. And what is 0 divided by 7? Well, that's just 0. So you can see that by using this definition, good over total, we do get 0, which is what we said should happen, that if something is impossible, the probability should be 0. Okay, now let's see if this definition is consistent with everything else that we've said so far. So over here, we said that it was unlikely that we pick a yellow marble. We said the probability should be somewhere between 0 and 0.5. Bigger than 0, but less than 0.5. Let's see if that actually happens when we use this probability fraction, good over total. So the probability of picking a yellow marble, take the number of ways the event can occur. So how many ways are there for me to pick a yellow marble? Well, if I pick this marble, then that's one way that it could happen. Another way that it could happen is if I pick this marble. So there are 2 ways for me to pick a yellow marble. So there are 2 good outcomes for me. I'm going to put that in the numerator. And in the denominator, I'm going to put the total number of possible outcomes. So all of the marbles, whether they're yellow or not. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the total is 10 here. And 2 divided by 10 is 0.2. So that would be the exact probability, in this case, of me picking a yellow marble. And it is greater than 0. 0.2 is greater than 0. Okay, and it is less than 0.5. Okay, so we could see here that just using our intuition, we can see that it is unlikely for us to pick a yellow marble. And now we have a mathematical analysis to go with our intuition. We do get a probability which is greater than 0, but less than 0.5. In this case, it would be 0.2. Okay, now, what if over here we have something which is just as likely as unlikely? Okay, what would the probability of picking a yellow marble here be? Well, we should get 0.5. Let's see if we do. So the probability of picking a yellow marble, I want to take all of the good marbles. So that means the yellow marbles for us. How many yellow marbles are there? 1, 2, 3, 4. So we'll put that in the numerator. Okay. Again, take the number of ways the event can occur. So if I want a yellow marble, how many different ways are there for me to choose a yellow marble? Well, I can choose this one, that's one way. I can choose this one, that's another way. Or I can choose this one, or I can choose this one. So there are 4 ways for what I want to happen. Okay, now how many total outcomes are there? What's the total number of different things that could happen? Well, I could pick this marble, I could pick this one, I could pick this one, this one, this one, this one, this one, or this one. So there are 8 different things that could happen here. And 4 divided by 8 is 0.5. Okay, if I wanted to turn that into a percentage, I would just take the decimal point and move it 2 spaces to the right, and that would give me 50%. Okay, but again, you can see that our intuition tells us when we look at this picture that since the number of marbles which are yellow is exactly the same as the number of marbles which are not yellow, then it's just as likely for me to pick a yellow marble as to not pick a yellow marble. And when that does happen, then using this definition, we do get a probability of 0.5 when we have a situation like that. Okay. Oops. Next one. Okay, so in this case, what's the probability of picking? So we said that obviously most of those marbles are yellow, so it is likely for me to pick a yellow marble. And when that happens, we will get a probability which is greater than 0.5 but less than 1. Okay, so let's see. The probability of picking yellow marble here, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 yellow marbles out of a total of 10 marbles. Just add that other one. Okay, so and 9 divided by 10 is 0.9. Okay, which is greater than 0.5 but less than 1. Okay, so when we have a situation where something is likely to occur, where most of the outcomes are good outcomes, but not all of them, then we will end up with a probability which is greater than 0.5 but less than 1. Okay? And finally, well, I keep doing that. Oh, okay, that's what I want to say next. Sorry about that. Okay, so I want to move on to this last one. So here we said that it was certainly, if I reach into this box and pick out a marble, certainly I'm going to get a yellow marble, right? And when I have a situation like that where something is definitely going to happen, then the probability that I'll get is 1. So let's see if I do in fact get a probability of 1 here. So in this case, the probability of getting a yellow marble, well, how many good marbles are there? There are 1, 2, 3 good marbles, because we like yellow marbles. Okay, so put that in the numerator. What's the total number of marbles in this box? Well, again, it's just 1, 2, 3. Okay, and what's 3 divided by 3? That's 1. So when we have a situation where every outcome is a good outcome, then plugging the numbers into this good over total formula gives us a value of 1. So anytime we have a situation where what we want to happen is definitely going to happen, then we will see that the probability is 1. Okay? Now, what if I did something like this? Let's just say that I was doing some other problem and calculating the probability, not necessarily this problem, but some other problem, and I got an answer of 2. Okay, how did I get that? Well, maybe I put a 6 in the numerator and I put a 3 in the denominator, and 6 divided by 3 is 2. So I'm doing a problem that my teacher gives me, and I say, okay, here you go, Mr. Teacher. The probability, my answer for this problem is that the probability is 2. Does that even make sense? Can a probability be greater than 1? Can I get a probability of, let's say, 2? Well, no, that probability does not even make sense. And I see a lot of students do probability problems and they'll get an answer of 2 or 3 or even something like 1.5, which is still bigger than 1. You can't get that. If you get an answer which is bigger than 1, then you went wrong somewhere. Because what does this mean over here? What if I had something like 6 in the numerator and 3 in the denominator? 3 would be the total number of marbles in that box, and 6 would be, let's say, the number of yellow marbles. So if I write something like 6 over 3, then what I'm saying is there are 3 marbles in the box, and 6 of them are yellow. That doesn't even make any sense, right? So it is impossible to get an answer here, a probability that is bigger than 1. 1 is the highest that you could possibly get, and 0 is the lowest that you could possibly get. If you're getting a probability which is negative, you made a mistake somewhere. And if you're getting a probability which is greater than 1, or as a percent greater than 100%, you made a mistake somewhere, okay? So for this case, again, the numerator would be 3, the denominator would be 3, and we would get a probability of 1 here. Okay, now I wanted to do a couple of other examples with some spinners. Okay, so first of all, what's a spinner? A spinner is something like this. So you have like a circular thing, you have an arrow in the middle, you flick the arrow, it spins around and around and around. And in this case, this is the spinner for the game of Twister. I don't know if you ever played that. Like put your right hand on red, put your left foot on green. If you've never played Twister, you probably don't know what I'm talking about, but that's okay. It's a fun game. Check it out. But all we really need to know right now is what a spinner is. It's just something like that where there's an arrow in the middle and you flick the arrow and it goes around and around and it lands somewhere. So let's say that we had a spinner like this, and I wanted to know the probability of, so here's the arrow which we're going to flick, and the arrow is going to go around and around and around, and it's going to land on one of these slices of the pie here. And you can see that we have pictures of dogs and we have pictures of rainbows here. What's the probability that this spinner, if we flick it, it lands on a rainbow? Well, what we'll do is we'll just count the number of rainbows. So there are 2 rainbows here. And we're going to put that over the total number of outcomes. So that's 1, 2, 3, 4, 5, 6. By the way, one common mistake that students make is in the numerator, they'll put the number of good things. For us, that's rainbows. Let's say we want to get the rainbows. So they'll put 2 in the numerator, and then in the denominator, this is a mistake now. In the denominator, a lot of students will put the number of bad outcomes, which in our case means the number of dogs, which is 4, and they'll put a 4 here. That is not correct. Okay, so the probability of something happening it's not good over bad, it's good over total. Okay, so for the total, we include both good and bad. All right, so the probability of picking a of that spinner landing on a rainbow would be 2 out of 6. Okay, 2 over 6, which is 0.3 repeating, which is approximately 33%. Okay, which is still unlikely. So if I spin that spinner, it probably will not, right? Unlikely meaning is greater than 0, but less than 0.5. So if I spin that spinner, it probably won't land on a rainbow. It'll probably land on one of the dogs, but it might land on a rainbow. So it's unlikely, but it's not impossible. Okay, now I brought that up. Here we have a situation where instead of pictures on the spinner, they're still pictures, but they're pictures of numbers. So instead of rainbows and dogs, we have 7s and 10s here. Now, what is the probability of spinning this spinner and having it land on a 7? Well, again, we would just count the number of 7s. How many 7s are on here? 1, 2. And we would divide that by the total number of outcomes. So that would be 1, 2, 3, 4, 5, 6. Okay, there are 6 slices of that pie there. And each landing on each slice is equally likely. Okay, so 2 out of 6 again, which is, again, 0.3 repeating, or approximately 33%. Okay, so this situation over here is very similar to this situation over here, but instead of rainbows and dogs, we have 7s and 10s. But there are still 2 7s, just like there were 2 rainbows over here, and there's still a total number of 6 outcomes that could happen, just like there were 6 outcomes that could happen over here. So why am I bothering to mention this example? What's the point of doing an example like this if I just showed you an example which was pretty much exactly the same? Well, my point in showing you this, after showing you this, is just to let you know that this is the same kind of situation as this. Because what a lot of students will do in a situation like this over here is, if I say, what's the probability of getting a 7, what they'll do is, instead of writing 2 here because there are 2 7s, they'll try to add up all the 7s, and they'll say, oh, 7 plus 7 is 14. Okay, and maybe in the denominator, they'll try to add up all of these numbers. Oh, 10 plus 10 plus 10 plus 10 plus 7 plus 10. Okay, so that's going to be 54. Okay, and then it'll do 14 over 54. But that is wrong. That is incorrect. When you get a problem like this, you have to understand that even though those are numbers that you see on the spinner, you should not treat them like numbers. You should treat them just like pictures like we have over here. Okay, so you don't have to do any calculations with the 7. All you have to know is how many pictures of a 7 are on that spinner. There are 2 of them, so the numerator would be 2. Okay, you should not be doing 7 plus 7. Back over here, did I try to do rainbow plus rainbow equals pretty? Did I put, oh, 2 rainbows, that's pretty. Did I put pretty in the numerator over here? No, I just put 2 because there were 2 rainbows, okay? So when you get a problem like this, please understand that you're not supposed to add up these numbers, okay? You treat it just like you would pictures, okay? And you just count how many there are. Okay, so let's continue now. Finally, you probably... I scrolled down to this before when I didn't know what I was doing. So now I actually want to do that. Okay, dividing the number of good outcomes by the total number of outcomes only applies when each outcome is equally likely. So let's talk about that. So take a look at this spinner that I have over here. Okay, I have another pie thing. Okay, when I say pie, I don't mean 3.14. I mean like a picture of a pizza pie, sort of. Okay, and I have a little arrow over here, and imagine we're going to flick the arrow, and it's going to spin around and around and around, and it's going to land somewhere. What would you say is the likelihood of the arrow of the spinner below that? Let me start again. What would you say is the likelihood of the arrow of the spinner below landing on red? Okay, so you have a spinner that looks like this. What's the likelihood that it lands on red? Would you say that it's impossible? It cannot land on red? Would you say it's unlikely? Would you say it's just as likely as likely? Just as unlikely as likely? Or would you say it is likely, it probably will land on red, but it might not? Or would you say that it's definitely going to land on red? It's certain. Which one of those would you say? Well, looking at this picture over here, you'd probably say, oh my goodness, so much of this pizza pie here is shaded red. So it is very likely that when we spin this spinner, it's going to land on red. Okay, and you would be right to say that. It is likely that this spinner will land on red. Okay, intuitively that makes sense because so much of the spinner is shaded red. Okay, if we were making a bet, and let's say for some, I don't know, for some Doritos or something, we're at lunch, I spin the spinner, and if it lands on red, I get the rest of the Doritos, and if it lands on green, then you get the rest of the Doritos. I'm more likely to win, right? Because so much of that spinner is red. But here's the thing. If we do this, the good over total, probability that it lands on red. Okay, well, how many red parts of the spinner are there? There's one red part, so we can put red, we can put one in the numerator, and we can put, what's the total number of parts of the spinner? There's one red, there's one green, there's one white. So there are 3 parts of that spinner there. Okay, 1 over 3 is, actually this is just a coincidence. It's the same as what we got before. Okay, again we get 0.33 repeating, which is about 33%. Okay, so 0.3 repeating, that is greater than 0, but it's less than 0.5. We would say something with the probability that's less than 0.5, but greater than 0, is unlikely. So if you're just using that good over total formula, you would say, wait a minute, the probability of me landing on red is actually unlikely. It's less than 0.5. But that doesn't seem to make sense just by looking at this picture over here. Okay, so where did we go wrong? Why is it that we can look at this picture and we know it's very likely to land on red, but when we do the calculation here, we get something which is less than 0.5, which is telling us that it's unlikely, not likely. What went wrong? Well, you probably guessed what went wrong is the fact that this red piece here is so much bigger than these other pieces. So that good over total formula, that only applies when each outcome is equally likely. Is getting green equally as likely as landing on red? No, because the green is so much smaller than the red. Is landing on white equally as likely as landing on red? Again, no, because the red is so much bigger than the white. So that good over total formula does not apply to this situation because not all of these pizza slices here are the same size. Okay, each slice has to be the same size, and therefore each outcome has to be just as likely as all of the other outcomes in order for that good over total formula to be applicable. So how could we calculate the probability of picking red here? It would not, I'm going to leave this up here, but I'm just going to put an X next to it to let you know that this is incorrect. How could we figure out the correct answer? Well, we would have to continue splitting this up until all of the slices are the same size. So I'm not changing how much red space is on this spinner, but I am splitting the spinner up differently until each slice of the spinner has the same area as all the other slices. Okay, so imagine that I drew that a little bit better. You can see that now each slice of the spinner is the same size. So each outcome here, this or this or this or this, every outcome is equally as likely as every other outcome. And now we can see, oh, okay, wait a minute. Now when I do the probability of getting red, well, there are 1, 2, 3, 4, 5, 6 red slices. And there is a total of 1, 2, 3, 4, 5, 6, 7, 8 slices. And 6 divided by 8 is 0.75. 0.75 is greater than 0.5, but still less than 1. So that makes sense because it is likely for me to land on red. So I should be getting a probability here which is greater than 0.5, okay, telling me that what I want to happen meaning landing on red, is probably going to happen, but it's still less than 1. It's not definitely going to happen because I could maybe land on green or white. Okay, so again, dividing the number of good outcomes by the total number of outcomes only applies when each outcome is equally likely. If we have a situation where one outcome is more likely than the other outcomes, we have to fiddle around with it a little bit and until we get it so that each outcome is equally likely. All right, so I am going to end the video there, and have a great day.